We are here with our first speaker. Welcome, Tobias Herrmann. He's Business Development Manager at ZESTRON, and he's talking about cleaning in scope of mission-critical electronics.
Hello. So, can you hear me? Okay. Thanks for the introduction, and welcome for the SMT for Aero Defense forum here at Productronica, and to my first presentation. So hopefully it is interesting for you. If you have any questions after the presentation, of course, please let me know. And what I'm going to talk about today is reliable cleaning in scope of mission-critical electronics, with the background of aero defense applications. And maybe ZESTRON is not a known company or known brand for everybody, so I'm very quickly introducing the company on one slide. So what we are doing is basically handling and working to have our customers, or to make reliable applications for our customers and to make the applications and the products of our customers reliable. And how do we do that? So in general, we are talking, when it comes to reliability requirements, we are talking about topics of humidity robustness. This is also, together with coating reliability, the main scope of today's talk. And then the technical cleanliness topics are also related to electronics reliability, so that's also what we are covering. What we are looking at in this scope are different surfaces, like PCBAs, SMT devices, and also semiconductor packaging devices like DCBs, or more complicated packaging for smart devices. And the contaminations that we typically look at are of filmic, ionic, and particle nature. So what we provide here, our main business is actually surface treatment and cleanliness, but around this topic, this main topic that I will also go a little bit more in detail today, we have an ecosystem of services. One I will also go in detail later is analytics and testing of devices to prove reliability and to control processes, and also coaching in a widespread to achieve process reliability, process stability, and for different applications. Our headquarter is not very far from here, so we are a German company based close to Ingolstadt. So it's very close, and we support from Ingolstadt complete Europe. But we also have technical centers in the US, including production, and the production in Malaysia and Asia, and a lot of technical centers in Asia, because let's face it, so most of the high volume production electronics is based in Asia, especially for semiconductor backend. So that's why our footprint is relatively big in Asia. And to ensure ongoing quality of our products, but also of our support, we are also certified. I think ISO 9001 is nothing very special, so most companies are following these quality standards, but we are also going in the environmental certification. Our products always had the scope of being environmental friendly, but now we are also going the next step in a certification to prove in a formal way to the customers. And very important, especially in scope of today's talk, for mission-critical products, is information security. So we now introduced information security certification according ISO 27001, and especially for the automotive market, customers are pushing to have even further improved certification, or not certification, but standards according to TISAX. So that's it for now for the company. Let's go into the topic finally. When I joined the company about little bit more than a year ago, I came from electronics design and not really from processing and from reliability topics in terms of humidity robustness. So I wondered, what are we actually talking about? So what's the issue? And I wanted to understand how can any issues that our company is actually focusing on happen. So what I show here, and I did it also for myself, is a diagram which is showing the humidity or the water content in the air on the y-axis and the temperature of the air on the x-axis. And the two lines that you can see here, a green one is 50% relative humidity, and the red one is the critical one, so that's 100% humidity, which is the dew point. So what happens with an electronic device? So let's say we are in the field in a mission-critical application, like a drone, for instance, and we're having the equipment with us. Now we want to start it. So it's about 15 degrees, for instance. We have 50% humidity in our air around that. So what we're doing is we're turning on the device. The device, any electronic device that is turned on, creates electric losses, so heats up. And if the air in a device, or air in general, is heating up, it has a higher storage capability for humidity. So the relative humidity might go down, but the water is going in the device because more water can be stored. And then, after we turn off the device, the electronics, the surfaces in the device are cooling down again. But depending on the design of our casing, of our system, the humidity might be trapped and cannot be exchanged as fast as is necessary. And then it can happen that during, on the PCBA, as you see here, comes into play. And this might not always happen in like one cycle, so this can also be over multiple cycles, so like a pumping effect can happen. So why is this an issue in mission-critical electronics, this kind of temperature changes and humidity buildup? So especially in the military sector. So we have a lot of mobile applications in a highly variable climate. So be it in a deployment, a regional deployment of jungles, deserts, or mountains. So the general environment that the devices are working on is very different. Then, of course, there are seasonal changes, like general, the seasons, but also weather and the day and night cycle, which is changing temperatures and humidities for the devices as an environmental condition. And then, of course, we have operative changes, like for drones, for instance, the flight altitudes. So there's a different environmental situation on the ground or several hundred meters in the air. And so these are all changes, challenges with operation condition cycles. On the other hand, devices that we are talking about today are have the requirement of a very long product life. So of course, if any, let's stay with the example of a drone. If the drone is applied and it is used in a, let's say, hostile environment, the lifetime might be very short. But the devices typically need to be built long in advance. They need to be transported to the application location, and they might need to be stored for a longer time under not very well-defined conditions. So the products also need to survive for a long time. And another issue that we see, again, being into autonomous system, but also communication devices, connected devices, a lot of miniaturization is happening because more intelligence, more functionality need to be integrated in devices. And so the electronics itself is getting smaller, pin pitches are getting smaller, so the whole electronics are getting more prone and more sensible to humidity issues. So now we talked about how humidity can build up, why this can happen in the devices that we are talking about today. But then again, the question is, okay, but what's the issue? So what can really happen if I have humidity, for instance, in my device? And in our company, we use this kind of triangle for a long time. What you see here as triangles is, on the one hand, to the top, the voltage, the operating voltage of a device, and then the power or the switching frequency and the computing frequency. So why is this relevant? Especially in the applications that we are talking about today, so military, defense, aerospace applications. Typically, we have not very high voltages. So most applications maybe run with battery. So the voltage level is relatively low. So we are more on this range. And this is where electrochemical migration on the surface is happening as a failure cause. And I will show you later what that means. But also we are running a lot of applications at high frequencies, like radios. And with radios, they are very, they have to work reliable in a high frequency range. So insertion losses as a issue, are a potential failure cause if humidity is coming on the electronics, because then the signals are not transferred in a way that they are intended to. So if we are going back to electrochemical migration, what does it mean? So here you see actually a power device, a discrete power MOSFET, under a test liquid. So this is water with some indicator for the pH value. And the video that you will see is only sped up by a factor of 3. So what you see now is happening in 1.5 minutes, roughly. So you see there's a small voltage between the terminals under humidity, and you see electromechanical migration from the cathode to the anode. So you see this kind of tree growth. And when I joined the company, actually, and I looked into this the first time, I was super shocked. I was super surprised that such a short circuit can happen in such a short time. And that's also why this topic is critical, because it's not really like an aging process and then you need humidity over a very long time on your PCB. It can happen very fast as soon as you have dewing on the PCBA. So how to prevent this failure? So you need to increase humidity robustness. For instance, by cleaning and sealing the PCBA. Sealing in the shape of conformal coating is very distributed, very common, if not a total standard in this kind of applications. So that's why I also want to talk a little bit about the coating process. So what does it do? First of all, the main job is to separate any humidity from the voltage levels and from the electronics, from the conducting parts, so that what you just saw in the video cannot happen. So this separation is the main task. And then, of course, especially if you want to go to miniaturization, there's also an additional benefit that you increase the insulation resistance, so you can build components more dense without any issues of electrical breakdown. But conformal coatings, actually every polymer is vapor permeable. So over the time, humidity can penetrate into the polymer, into the coating, and also through the polymer. So this is normal, it cannot be changed, so this is for every polymer. So that means that your process of coating needs to be very stable and has some issues, some potential issues that can happen. So first of all, what you see here is delamination that you want to prevent. So the coating needs to really stick to your surface, so that you don't get any air pockets or bubbles below the coating where humidity can gather and build this kind of humidity pool as you saw in the video. Then you also need to avoid, together with the first point, any hygroscopic contaminations below the coating. Because if you have contamination there, for instance ionic contamination, that is actually pulling humidity through the polymer because it is hygroscopic, then the reliability and the withstand time, let's say, of the coating is reduced. Of course, you also need to prevent any cracks or issues of the coating itself. So cross-linking need to be optimized. And there are several risks for that. One is process-related, like the drying process. but the other one is also related to contamination on the surface, which can prevent proper cross-linking of polymers during the drying process. And then, of course, again, the process needs to be stable so you don't have any bubbles, but that is a, let's say, a real process optimization topic. So again, to have a really reliable coating, you need to make sure that the surface is well prepared, and this is done by cleaning. But now, in this scope, for this presentation, the target is mission-critical electronics. So that means the customers and the projects are always of a very sensitive nature. And this comes with a few challenges. Also, in this market, especially in the aerospace market, the volumes are not as high in the production. So we cannot compare it to a standard consumer or automotive production. So the PCBAs, the amount of PCBAs that are produced are typically lower, and we have a low volume, high mix production. So that means the processes that you apply need to be very flexible to different material mixes and to different designs. There are typically also different materials included because many customers are using a production both for the civilian sector but also for the aerospace and aero defense sector. And in the aero defense sector, a lot of leaded solder pastes are still used. So the requirements also on cleaning and coating are different depending on the materials that are used. Then, especially for radio frequency systems, for higher frequency systems, the designs on the PCBA can contain a lot of, let's say, sensitive surfaces, like precious metals or special metals, let's say, that you need to protect during your processes. So there's no oxidation, for instance, or other chemical interactions. And then, last but not least, as I mentioned in the beginning, typically, all the projects that we are talking about in this sector are very secret and under confidentiality. So sometimes it's really, really difficult to exchange relevant information with the customers in these kind of projects because of the sensitivity of the nature. Of course, we are working on that, as I mentioned, with the ISO 27701 to build up the trust and the processes to handle confidential topics, but still there's a very it's very tricky to really get the designs that you are talking about on hand. So, what can be possible solutions for these challenges? As I said in the beginning, low volume, high mix. Typically, that means that regarding the technology in the cleaning processes that you are using, a batch process is more common than an inline process. I mean, for the people that are not really aware and not involved in the cleaning processes, so just to give a small explanation, a batch process basically means that you had a device or a cleaning machine, you put your goods, your PCBAs into it, and then typically a cleaning process consists of several stages. So you have a wet chemical cleaning, and then afterwards you need to do a rinsing by DI water, and then you need to do a drying of the PCBA. So a batch machine typically includes all these phases in one chamber, so it has less space need, but it is also quite flexible because you can adjust the different parameters of the single steps depending on the design that you are currently loading in the machine. Whereas an inline machine is basically running completely through, so all the goods are coming in, running after each other through different, let's say, locations, like in a solder oven, and then getting out. And for this kind of processes, it's much more difficult to adjust the parameters for the cleaning for low volumes and for changing designs. So the process optimization, again, is important, but then also, it's difficult to really get the designs from customers due to confidentiality. So one potential solution to that is that test cards are created which represent, let's say, the cleaning challenges that you typically face in the final design. So that means that the solder pastes that are typically used are used on the test PCBs, that you have ICs, for instance, that represent the size and the standoff, which is the difference between the PCBA and the underside of the microcontroller, for instance, so that this is represented properly on the dummy board, and also connectors that are, for instance, cleaned, or other devices that might be critical, so that these test boards are really representing the, let's say, the critical points of the final design. Then the validation of processes is very important, and I mentioned that in the first slide where I said we are also offering analytics support. So to see really the contamination on the PCBA, on the design, before cleaning process and after the cleaning process, to validate that, to choose the right process, of course, but also to prove the cleaning success for a qualified process. This is very important. And we can offer that, of course. And this is also possible, for instance, for IC, so ionic contamination measurements, by doing an extraction at the customer side with the final design. And then this can be sent to us so we can do analysis, for instance. Yeah. And last point also, part of what I just said, the monitoring of the process once it's designed or once it's developed and validated, you need to monitor. And also these, their solutions are available, and we can discuss in detail if you want. So just regarding the cleanliness process itself, or the cleaning process itself, there are 4 major parameters that you need to keep in mind, that need to be monitored. It's called the so-called Zinner circle. So you have always mechanics, kinetics, how you apply the cleaning chemistry, as you see later. So there are different methods. I will show a bit more details later. Then the time, so how long is a cleaning or rinsing process running. The temperature. So this is also very physical, very basic physical. So the higher the temperature, the faster a chemical reaction is happening. But also you have some backsides because materials can be sensitive to high temperatures. So this needs to be balanced, basically. And then, of course, very important, what kind of chemistry are you using in your process? Because that depends a lot on the contaminations that you have to remove, and also the materials that you have on the system, so that they are compatible and not damaged. Yeah, so how to find out the optimal process? Typically, this is done by trials, of course, with some pre-knowledge, let's say. So, for instance, at our site in Ingolstadt, or close to Ingolstadt, we have a big technical center with different machines where we can do cleaning trials with our chemistry for customer boards. And we also have big databases, for instance, of solder pastes and other materials, also coating materials. So we know already from experience which processes are typically working together with which challenge. Okay, so regarding mechanics in the Zinner circle I just mentioned, so there are different methods of agitation, as you so call, which is the process of basically moving the cleaning and the rinsing fluid in the cleaning machine. So you have on the one side immersion cleaning, where you dip the PCBA, for instance, in the cleaning media, and then you have some agitation by either air bubbles or ultrasonic devices or spraying under air. Or you have a so-called spray in air process, where the goods are basically still in air in a holder, and then you spray the medium onto them. So these are the 2, let's say, main differentiations. And then regarding chemistry, not only from our side, but generally in the cleaning market, you can differentiate between 2 groups. First one is maybe more, let's say, historical, but still used a lot, solvent-based processes. So here the downside can be, of course, operator safety sometimes, and also the outgassing of the products. So the trend in the past went more to water-based cleaning agents because this is easier to handle. And you see here also the typical applications. So on the left side, there are mainly metal cleaning, maintenance cleaning applications. And on the right side, when it comes to more complex solutions like PCBAs with a very high material mix on the cleaning goods, then you are working on water-based designs typically. Okay, so one last, or not the very last point, but one major last point is the monitoring of the processes, as I just mentioned. So how do you make sure that the process, once you have it validated and introduced in your production, is really working reliable? On the first hand, regarding analytics possibilities, we have the process control itself. So that means typically you have the cleaning medium, which has for the water-based products a concentration, which is the mix or the percentage of the cleaner in the water. So you need to control the concentration of the cleaner in the water. You also need to check pH values because this can change depending on the contaminations, and you need to measure solid contents also. Then, during the validation phase, but also after the validation in the mass production side, you need to check the surfaces on the contamination and cleanliness. So for this, there are different methods, like normal microscopies, contact angles for surface energy, ROSE and IC tests for ionic contamination, and for further, let's say, analysis to really find the contamination materials and root cause analysis if you have some issues, the FTIR for organics analysis, and the general EDX are very helpful. So you can look at the surface, check what kind of contamination do you have there, and has it been removed with the cleaning process. And then you can also do further validation by quick tests. So this is partially easy to handle, like the top one. So ZESTRON involved implemented that, invented these tests, like the flux test and the resin test, which is a very, same as the coating layer test, very easy optical test where you have a test liquid that you put on your PCBA and you can check, okay, do you have some flux residues, resin residues, and you have a color marking, or in case of the coating layer test, if you have any weaknesses in the coating layer, the test liquid can penetrate the coating and then reacts with the metal below, and you have a optical feedback if you have some weaknesses. And if you want to go deeper into that, there's also more reliable tests, like the coating reliability test. So you're putting the device underwater, under voltage, and you see if the coating is really protecting your device. And if you see any weaknesses in terms of bubbles or increased leakage current, this is an indication that maybe you need to improve your process. Okay, so in the last slide, I have some more details here on these testings. But I think this is also in the handout. I don't know if you have this available later, but you can also check back with us. So there's some routine checks, as I just mentioned, the so-called ROSE test for ionic contamination. This is a test where you put the PCBA under solvent or not test liquid, basically under a water mixture. And then the ionics or ions are washed out, and basically you measure the conductivity of the remains, and then you get a good picture if you have how big is your ionic contamination. So for normal process monitoring, this is good enough because you can check, depending on the limit that you set before, if your process is still stable. And same with ink tests for surface energy. And yeah, so these are the very, very easy tests, and flux and resin tests. And in the, as I already mentioned, during the validation, you can use ion chromatography, where you get really the information on the different ions, which gives you again an indication where a contamination comes from. So depending on your solder paste or flux that you have on the PCBAs or other materials, you get an indication on what's actually the issue, what do you have to remove. And for the SIR test, this is also a test which is used for the qualification of a process, especially of a coating process, where you have a comp structure and then apply basically the coating and put the test structure in a climate chamber, and then you can also see if there's an increased leakage current. And once you pass this test, you know, okay, the process is fine. So this is again part of the validation. Okay, and the last slides here, as I mentioned, regarding coating checking from our side. So the coating layer test is a self-test that you can apply on your own. But we also have our R&S team, which can support with more in-depth tests, like the coating reliability test, if you want to validate your processes. Okay, so I hope I'm in time. So my time here is saying 0. The other one is saying I'm in 30 minutes, so I should be done now. Thanks for listening. And if you have any more questions regarding cleaning processes and reliability, then we are happy to have you at our booth. And I will be there also back, and my colleagues are anyway here. So if you have questions, please contact us there. Thanks.